Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. In the previous session, we discussed about two types of flip-flops, D flip-flop and JK flip-flop. We learnt the advantages of JK flip-flop over SR flip-flop and D flip-flop. We saw how a JK flip-flop can be constructed using NAND gates. In this class, we will continue with the JK flip-flop constructed using the NOR gate, and we will also discuss about the next type of flip-flop, T flip-flop. So, as I said in the earlier session, the JK flip-flop, in order to avoid the indeterminate state, uses the previous state values also as its input. When we saw the construction of JK flip-flop using NAND gates, I had told you that the previous value Q has to be connected to the input K and the previous value Q complement should be connected to J. This rule applies in the construction of NOR gated JK flip-flop also. The block diagram of the JK flip-flop is all the same irrespective of whether we are using NAND or NOR gates. They have two inputs J and K similar to the SR flip-flop and gets activated only on the arrival of the clock pulse. Now, let us focus on the working of NOR gated JK flip-flop. Look at the diagram. You can see the output Q is connected back to the input K and Q complement is connected back to the input J. The input gates are different. They are two AND gates, not the NAND gates, as we have seen in NAND gated JK flip-flop. And the SR latch inside the JK flip-flop is built using two NOR gates. In order to comprehend the working, you have to recall the truth table of NOR gates and AND gates. If either or both inputs of NOR gate is 1, then it will produce 0 as its output. The AND gate will have 1 as its output only if both of its inputs are 1. Let us assume that clock is equal to 1 and analyze how the JK flip-flop behaves for different combinations of input values. Consider the first case, J equal to 1 and K equal to 0. Since K equal to 0, the input gate connected to the K will have 0 as its output. What happens to J? It has two inputs that are 1. So, to know its output, it has to depend on the previous state value Q complement. Now, there are two scenarios. The previous state values could be Q equal to 0 and Q complement equal to 1, or it could be Q equal to 1 and Q complement equal to 0. Now, assume that previous state value was Q equal to 0 and Q complement equal to 1. Then what happens to J? Its third input also becomes 1 and the input gate will now have 1 as its output. Look, inside the JK flip-flop, we have a NOR gated SR latch which has its S as 1 and R as 0. Recall the characteristics table of NOR gated SR latch. If S equal to 1, then it will set the flip-flop. So, the output of JK flip-flop in this case will be Q equal to 1 and Q complement equal to 0. Now, if the previous state value of the JK flip-flop was Q equal to 1 and Q complement equal to 0, what happens then? Look at the diagram. The J input gate will also turn out to be 0 because Q complement is 0 now. What happens when NOR gated SR latch has its both inputs 0? It will retain the previous state, that is, the output of the JK flip-flop will be same as the previous state Q equal to 1 and Q complement equal to 0. After considering the two scenarios, we can infer that when J equal to 1 and K equal to 0, the flip-flop will turn to a set state irrespective of its previous state values. Let us see the next case, J equal to 0 and K equal to 1. Here also we have to analyze both scenarios of the previous values. Here the input j is 0, which makes the output of the j gate as 0. The input gate connected to k has two of its inputs as 1. So, it has to look into the third input, which is the q value of the previous state. In the first scenario, let us assume that q equal to 1 and q complement equal to 0. Hence, q equal to 1. Then the k gate will have a 1 as its output. Now, you have an SR latch with S equal to 0 and R equal to 1. What does the truth table of an NOR gated SR latch says? Such values of S and R will reset the flip flop, that is q equal to 0 and q complement equal to 1. So, when you had the input 0 at j and 1 at k, it turned the flip flop to a reset state. Now, let us see what happens when the previous values are q equal to 0 and q complement equal to 1. Look at the diagram. The inputs to the j and k gates have a 0, which will turn both the outputs to 0. What happens when the NOR gated SR latch has two of its inputs in the low state? It does not do anything new, but just remains in the previous state, leaving the state of the flip flops as q equal to 0 and q complement equal to 1. Hope you understood that even when the previous values are different, the JK flip flop turned to the reset state when its external input j was 0. What about case 3? When j and k are 0? Since the inputs to the AND gates are 0, the outputs to SR latch will also be 0. Just now we saw that when the inputs to the SR latch are both at low state, it will remain in the previous state itself, no matter whatever be its values were. See the diagram depicting both scenarios of previous values. It did not change the final output of the flip flop. So, we can infer that when the external inputs j and k to the JK flip flop are 0, the flip flop will retain its previous state. The last case is when j and k are 1. The j and k gates have two of its inputs as 1. So, to determine its output, they have to check the previous values of the flip flop. Whenever the previous value of q is 0, the input R to SR latch will turn to 0, which in turn will set the flip flop. If the previous value of q is 1, it will enable the input R of the SR latch, which will reset the flip flop. Look at the outputs produced when j and k are 1. They are complemented the previous state values. When q equal to 0 and q complement was 1, the flip flop produced the current state values as q equal to 1 and q complement equal to 0. And when the previous values were q equal to 1 and q complement equal to 0, the current state value became 0 and 1 respectively. So, it says that whenever both the inputs to j and k are high, it complements the previous state values. We had already seen the characteristic table of JK flip flop while we constructed it using NAND gates in the last session. Let us verify it again, whether we have got the same outputs for those inputs when we constructed it using NOR gates. When j and k are 0, there was no change at all for the flip flop, and when both changed to 1, we obtained the complement of the previous state. And when j equal to 0 and k equal to 1, the flip flop went to reset state and turned to the set state while j equal to 1 and k equal to 0. One more point to be analyzed here is that what happens if the clock pulse is 0? I had not mentioned this in the last sessions too. Now, let us see what will happen here when the clock equal to 0. One input to both AND gates becomes 0, which will produce 0 as the inputs to the SR latch. And we all know that for a NOR gated latch, when its both inputs are 0, it will continue in the previous state itself. Recall, we had learned that the flip-flop is a stable device which produces output only at discrete intervals of time. Yes, that means it will change its state only when the clock is positive or at the state 1. You might be wondering whether the same process happens in a NAND gated JK flip-flop. There we were using 2 NAND gates as input gates. So, a 0 at their input will definitely produce a 1 at their output, and you all know that a NAND gated SR latch will continue to remain its previous state when its inputs are at high level. So, we can reach into the conclusion that the JK flip-flop will continue to remain in its previous state when the clock is equal to 0. So, hope you are clear with JK flip-flop now. Let us move on to the last type flip-flop, that is T flip-flop. T flip-flop is a single input version of JK flip-flop. It combines the J and K inputs and presents it as a single input T. We have come across similar kind of flip-flop, the D flip-flop, where 2 inputs are combined into 1, but with a difference, an inverter was added between the inputs. What is the peculiarity of this new flip-flop? In what context will it be used? Let us study these aspects now. Look at the block diagram of T flip-flop. It has a single input and also has a clock pulse to enable it. The outputs are the value stored in the flip-flop Q and its complement Q complement. As we had mentioned in earlier sessions, the flip-flops can be constructed using NAND gates and NOR gates. Our next discussion is about the construction of T flip-flop using both of these gates. Let us see how a T flip-flop can be built using NAND gates. Look at the diagram. It is the JK flip-flop where the 2 inputs are joined together to form a single input T. Since the inputs are joined, the number of combination of input values are reduced to 2, that is when T equal to 1 and T equal to 0. Let us see these 2 cases assuming that the clock pulse is high. Case 1, when T is equal to 1. Since both the inputs to the NAND gates are 1, we need to check the previous state values to determine the output. Let Q equal to 0 and Q complement equal to 1. Then Q connected to the second NAND gate will produce 1 and the first NAND gate will have the value 0 as the output. What happens to the NAND gated SR latch when its inputs are S equal to 0 and R equal to 1? It will turn the flip-flop to the set state. Next, let us check what happens when the previous state is Q equal to 1 and Q complement equal to 0. Will the flip-flop turn its state to the set state? All the other flip-flops we had discussed earlier attained the same state irrespective of their previous values for all the input combinations. Will it happen here also? Look at the diagram. The NAND gate connected to the Q will have the output 0 and the NAND gate connected to Q complement will have the output as 1. The inputs to the SR latch is now S equal to 1 and R equal to 0, which will reset the flip-flop. Not here, the flip-flop was not set, it was reset. So, when the input to the flip-flop is 1, it behaved in 2 ways depending on the previous values. Shall we have an examination on the previous values then to generalize the performance of the flip-flop? When Q was 1, the current state value was 0, and when Q was 0, the current state value became 1. Then it is very clear that the flip-flop complemented the previous state when their input to the circuit was 1. In that context, what happens when the input to the circuit is 0? Since the input has a 0, the first two NAND gates are going to produce a 1 as its output. What happens when a NAND gated SR latch has its both inputs as 1? It will continue to remain in its previous state. Here, the previous state values are not necessary to know the current state values because the inputs are 0, which will always set the SR latch in the high state. Look at those two diagrams and understand how the T flip-flop is working when the input is 0. Here we learnt that the T flip-flop complements its state when T equal to 1, else remains in the same state when T equal to 0. Let us see the construction of the T flip-flop using NOR gates. Here is the logic diagram of the T flip-flop using NOR gates. At the input, we have two AND gates and the JK inputs are combined. This part of the circuit is then connected to a NOR gated SR latch. Let us see the working now. We will start with T equal to 1. The two diagrams shows the state of the flip-flop when the input is high. It is complementing the previous state value as we had seen in the NAND gated T flip-flop. Since two of its inputs to the AND gates are 1, it checks the previous state of values. When Q equal to 0 and Q complement equal to 1, the first AND gate produces 0. Since Q equal to 0 and the second gate has 1 as its output because Q complement is equal to 1. The NOR gated SR latch sets the flip-flop when S equal to 1 and R equal to 0. When Q equal to 1 and Q complement equal to 0, the second AND gate connected to Q complement produces 0 and the first gate has 1 as its output. When the input to the NOR gated SR latch is 0 and 1 for S and R, it will reset the flip-flop. Yes, when T is 1, the flip-flop moves to the complemented state of its previous value. What if T equal to 0? As we have seen earlier, the flip-flop should remain in the previous state itself. Let us verify this. The output values of the two input gates are 0 because we are having 0 as its input. Now, the situation became simpler. Having two low inputs to the SR latch will keep the flip-flop in the previous state itself. Check out these two diagrams. So, the T flip-flop is used when you want to toggle the flip-flop when the input is 1. The term toggle stands for the complementing action. The first character of the term toggle is used to represent this flip-flop and hence it is called as T flip-flop. Let me mention one more point. What happens when the clock is equal to 0? In the NAND gated T flip-flop, the inputs to the SR latch will remain at 1, which will retain its previous value, and for the NOR gated flip-flop, the inputs to the NOR gated SR latch are 0, which will also hold the previous value of the circuit intact. Now, here is the characteristic table of the T flip-flop. See the table. The first row says the state of the flip-flop remains 0 when the input to the T flip-flop is low, and the second row indicates that the flip-flop complements its state when the input is in a high state. With this, we have come to the end of this session. So, to summarize, let us have a recap on the topic flip-flops. The flip-flops are binary cells which can store one bit of information. These flip-flops are stable and predictable because they change their output only at discrete and regular intervals of time, that is when the clock pulse is applied. Later, we discussed about the different types of flip-flops, SR flip-flop and its modified version D flip-flop with a single input. The shortcoming of these two flip-flops were rectified in third flip-flop, the JK flip-flop. At last, we discussed about the T flip-flop, which is used to complement the state of the flip-flop each time its input goes high. Let us talk about the triggered flip-flops in the next session. Thank you for watching. See you in the next session. Bye.